So is my screen visible?
Yes.
Okay. So today we will be discussing week 3 assignments from previous year for NPTEL PMRF course Introductory Organic Chemistry to August 2023. The course instructors are Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself Anisha Suresh, PMRF TA for this course from IIT Bombay. So we will summarize the week 3 contents first, followed by we will solve the previous year questions uh, that are given in previous year assignments. So coming to the summary of week 3, uh, in this week, basics of carbonyl compounds were discussed, followed by addition reactions on carbonyl functional group and then nucleophilic addition reactions and its stereochemistry. So coming to the basics of carbonyl compounds, additions to carbonyl compounds generally consist of two mechanistic steps. So first will be the nucleophilic attack on the carbonyl group, followed by protonation of the anion that results. So we can see here. So here this is the carbonyl compound. It was treated with sodium cyanide presence of H2SO4 and H2O. So sodium cyanide, the Cn minus will be the nucleophile. So Cn minus will add into this uh, electrophilic carbon center, and this carbon oxygen double bond will break and this electron density will shift towards the oxygen. So here the oxygen will be now an anion. It will be having the negative charge on itself. So this oxygen will abstract a proton from the medium. Like here the medium is containing acid. So it will abstract proton from the medium and it will give the alcohol, cyanohydrine. So is the mechanism clear? First it will undergo nucleophilic addition of Cn minus to the carbonyl group. Here the carbonyl carbon is the electrophilic center. So the cyanide, which is the nucleophile, will be attacking on the carbonyl carbon. The carbon oxygen double bond will be breaking and this electron density will be shifting towards the oxygen. So now oxygen will be having a net negative charge on itself. So this negative charge will abstract proton from the medium so as to neutralize itself and results in the formation of cyanohydrine. So this is the basic mechanism of addition reaction to carbonyl compounds. This is clear, right? Now coming towards the orbital picture of this carbonyl compounds, we are having formaldehyde. So the sigma bonding in formaldehyde will be like there will be sp2 hybrid. This carbon is sp2 hybridized. This carbon is sp2 hybridized and this oxygen is also sp2 hybridized. So sp2 hybridization means it will be having a planar geometry. So these are the sp2 hybridized orbitals. So one of the sp2 hybridized orbital will combine with the sp2 hybridized orbital of the oxygen forming a sigma bond here. CO sigma bond made up of the two sp2 orbitals. One of the sp2 hybridized orbital of this carbon and the sp2 hybridized orbital of this oxygen will combine to form the CO sigma bond. Then it will be having two more sp2 hybridized orbital. So it will be combining with the uh, hydrogen atom to form this carbon hydrogen sigma bond. So this bond angle will be 120 degree. For sp2 systems, the bond angle will be 120 degree typically. So this bond angle between this carbon hydrogen and the hydrogen will be 120 degree. Then the oxygen will be having remaining two sp2 hybridized orbital. So it will be containing lone pair of electrons. Remaining sp2 orbitals on oxygen contain lone pair of electrons. So now there will be p orbitals remaining in carbon and oxygen. So the pi bonding will be resulting from the remaining p orbitals. So the major contribution for pi bonding will be from the oxygen and minor contribution will be from carbon. So the CO pi bond is made up of the two p orbitals of carbon and oxygen. So here we are clear about how sigma sp2 sigma orbital is formed by combination of the sp2 hybridized atom of carbon and oxygen. Now the pi bonding is resulted from filled pi orbital. So here we can see carbon will be having one electron and oxygen, which is electronegative, will be having one electron. So it will combine to form molecular orbitals. Sorry, here there will be no electrons. So these electrons will be combining to form the uh, pi orbital. This is pi orbital, and this will be the pi star orbital. So pi orbital will be having major contribution from oxygen as it is energetically similar to that of oxygen. And in case of pi star orbital, it is energetically closer to that of the carbon. So it will be having um, property similar to that of the carbon. So here we can see this is the pi orbital and this is the pi star orbital. So here pi star orbital major contribution will be coming from the carbon, uh, as we have seen here, and in this case the major contribution will be coming from that of the oxygen. So this will combine, resulting in the formation of pi orbital, and this will result in the pi star orbital. So this is the typical molecular orbital diagram of CO bond. This is clear?
Yes, ma'am.
Now we will see addition reaction on carbonyl functional group. So this compound benzyl aldehyde. So this is referred to as prochiral, as the addition of Cn minus to it will result in the generation of a new stereogenic center here. Here all the four groups are different. So this will be a chiral center or stereogenic center. So this compound is referred to as prochiral because this addition reaction will lead to the generation of a chiral center here. So that is why this is referred to as a prochiral molecule. Now we will see here in the case of acetone, the center is not prochiral because when we add Cn minus, it will result in the formation of this cyanohydride, where there will be two similar groups, that is two methyl groups. So this center will not be prochiral. So now we will see the example of a glycine. So if we replace the green hydrogen with a group called a G, make G higher priority than hydrogen. So this G is a group having higher priority than hydrogen. So what will be the nomenclature? How we will assign nomenclature? So we, as it is shown here, the first priority will goes to NH3 plus. Then comes C double bond O minus. Then, as we have mentioned, G is given higher priority than hydrogen, and then the least priority will be coming for hydrogen. So, 1, 2, 3. It is anti-clockwise rotation, right? 1, 2, 3. So, this new center is referred to as S. So, this green proton is referred to as Pro S. This replacement of this green proton is resulting in a compound having S chirality. This S. So this green proton is referred to as Pro S. So is it clear how we are assigning the priorities? That is clear, right?
Yes. Yes.
Okay. Now, if we consider this glycine again, and if we are replacing this orange proton, orange hydrogen by a group G, where G is having higher priority than hydrogen. So, as labeled previously, the priority will be as NH3 plus will be having 1, C double bond O minus will be having 2, G will be 3, and hydrogen will be 4. So, here also uh, it will be anti-clockwise rotation, but since the low priority group is towards us, it will be opposite of that. So, it will be R. And since this compound is R, this proton will be called pro-R proton. Clear, right? Prochiral it is clear.
Yes, ma'am.
Okay. Now we will see the enantiotopic phases of benzaldehyde. So if we are viewing from this side, if we are viewing the compound from this side, like this. So here the carbonyl will be coming in this side, and this proton will be coming towards our left hand side, and benzyl will be phenyl will be coming towards our right hand side. So if we assign priorities, this will be given 1, oxygen will be given 1, pH will be given 2, and hydrogen 3. So this is clockwise rotation, and this phase is called rephase. Clear? We are mentioning about enantiotopic phases of benzaldehyde when we are viewing from this direction. So carbonyl group will remain as such in the plate. This hydrogen will be towards our left hand side, and phenyl will be towards our right hand side. So if we are assigning priorities, this oxygen will be getting 1, phenyl will be getting 2, and hydrogen will be getting 3. So this is clockwise rotation. So this is pre-phase. And if we are viewing from this side, opposite side, like this. So now our right hand side will be hydrogen, and our left hand side will be phenyl, as like this. So 1, 2, 3. This is counterclockwise rotation. This phase is referred to as psi phase. If rotation is clockwise, it is rephase, and if it is anti-clockwise, it is called a psi phase. So these are enantiotopic phases. So this is a prochiral molecule. So its phases, depending upon from where we are seeing it, are called rephase and psi phase, depending upon the direction of this rotation. Rephase and psi phase is clear.
Yes, ma'am.
Okay. Now we will see Felkinan model. So the lowest energy conformations of a carbonyl compound. This is the carbonyl compound that is given, which is having a chiral center already. The most important conformations of a carbonyl compound with a stereogenic center adjacent to the carbonyl group are those that place the largest group perpendicular to the carbonyl group. So, if the largest group, which is referred to as L, is perpendicular to the carbonyl group, that will be the favored conformation. So, here we are referring to carbonyl compound which is having a stereogenic center that is adjacent to the carbonyl group. Okay, so Felkinand model is referring to a carbonyl compound with a stereogenic center adjacent to the carbonyl group. So here the most favorable conformation will be when the large group or the largest group is perpendicular to the carbonyl group. So this will be one conformation that is favored, with the largest group perpendicular to the carbonyl. and the smallest group and medium sized group in this fashion. And other conformation which is resulted by rotation of this groups, rotation of the back carbons. So we are rotating it in this fashion. So if the largest group is coming perpendicular in this side, so the smallest group will be nearby to that of the carbonyl and the medium group will be away. So this is two conformations that are referred to as some most important conformation of the carbonyl compound, because here the largest group is perpendicular to that of the carbonyl group, hence this will be one of the stablest conformation of carbonyl group. So now if we see the approach of a nucleophile, now if we consider nucleophilic addition to the carbonyl group, nucleophilic addition to the carbonyl group. So here phenyl group is the largest group. In this case, phenyl group is the largest group. This methyl group is the medium group, and this hydrogen is the smallest group. And in this case, smallest, and this is the medium. So we are representing both these conformations here. So, for nucleophilic addition to a carbonyl group, the nucleophile should approach from some certain angle. So, that angle is referred to as Bourguignon angle, which will be between 105 to 107 degree. So, in Claydon, it is referred to as 107 degrees. In some textbooks, it is referred to as 105 degree. So, the nucleophile will be approaching from at a angle of 105 to 107 degrees to that of the carbonyl group. So it can approach from this side, and in this case from this side and this side. So here if we consider, when the nucleophile is approaching from this side, here phenyl group is there. So it will cause steric hindrance for the nucleophile. And here if we consider the nucleophile approach, here the nucleophile is approaching in this side, and the group that is near to that of the nucleophile will be hydrogen. So this will be an unhindered approach. Now if we consider this case, if the nucleophile is coming in this direction, it is close to the phenyl, so there will be sterical hindrance from the phenyl. And if it is coming from this side, it is close to the methyl group, so it can face steric hindrance from the methyl group. So we can see the black flight path is the best. That is, the approach of the nucleophile from this side is the best. The three brown flight paths are hindered by phenyl or methyl. So here uh, nucleophile is hindered by the methyl group. This case and in this case, the phenyl group is hindering the nucleophilic approach. So the black flight path that is represented here will be the best path for nucleophilic addition. Is this clear?
Yes, ma'am.
So this is basically the Felkinand model. We will be solving problems based on Felkinand model in today's session. Now coming to another case where uh, SN2 reaction is taking place for a compound having this benzoyl group attached to it. So here what is happening? So this is the pi star of the CO double bond, and this is the sigma star of the CCl bond. So in case of SN2 reaction, we have seen that the nucleophile will be coming and attacking from the sigma star of CCl bond. So in this case, what will happen? The pi star of the CO bond and the sigma star of the CCl bond, it can combine. We can see here both are having the same phase, right? This sigma star and this pi star, they are on the same phase, so they can combine. So this will be the combined pi star plus sigma star. So nucleophilic attack occurs very easily here. Why? So this is the pi star of the CO bond and this is the sigma star of the CH bond. If it combines, the resultant pi star plus sigma star, the new molecular LUMO, it will be having lower energy. If the energy of the LUMO decreases, it will be more reactive. For a reaction to take place, it should have lower LUMO, higher HOMO. LUMO means lowest unoccupied molecular orbital. HOMO means highest occupied molecular orbital. So this is the electrophile in our case. So we will be considering LUMO for the electrophile. So here the energy after combining will be lower for the LUMO. Hence it will be more reactive. Now another case is if we are having a chelating group. So what will be the like what will be the addition mechanism, nucleophilic addition mechanism. So here this SPH, this S is a group that is able to chelate. So if chelation is not taking place, as we have seen in the Felkinan model, addition is most probably taking will take place from this side, right? We have seen here addition is taking place where there is less hindrance. So here there will be less hindrance in this case. If chelation is not possible, so addition will be taking place from this side. So here the SPH will be also having lone pair. Oxygen is also having lone pair. It can chelate with metals like zinc, etc. So it will rotate in some degrees. So it will rotate. It will coordinate with zinc. So now this hydrogen is in this side. Since this rotation is taking place, hydrogen will come to this side. Now if we have NaBH4 or something for reduction reaction to take place, the hydrate will go and attack from this side. So now if attack is taking place, hydrate will come over here, OH will shift here and there will be uh, pH here. And if we redraw it, it will give this compound. So we will discuss in detail how to redraw and all when we will be working out the problems with this. So now we can come to the problem solving session. So this is all about the summary of week 3. And for references, you can follow Claydon Organic Chemistry chapter 6 and chapter 34. In chapter 6, they will be discussing about addition reactions on carbonyl compounds, and in chapter 34 they will be discussing this stereoselectivity and all, like based on Felkinan model and all. Okay, so summary is all clear, right? Now we can move on to solve the problems. Can we?
Yes, ma'am.
Okay, now this is the first question. For which of the following equilibrium the K equilibrium will be less than 1? So here we have CF3 on both sides plus H2O, it will give this product. Here we are having CCl3 instead of CF3 and it will give this product. So this is basically hydration reaction. So in which of these case the K equilibrium will be less than 1? That is the question. Then there is CH3 plus H2O, it will give this product. Then F double bond OH. So plus H2O, it will give this product. So for which of the following cases K equilibrium will be less than 1?
Third option.
Hmm?
Option third option.
Option 3. Yeah. What will be the probable reason?
Carbonyl less electro.
Okay, okay. So here we can see this is a carbonyl that is given. So we are doing hydration reaction. So this is an equilibrium reaction. So it will result in the formation of this hydration product. If it is acetone, the equilibrium constant K will be 0.001. In case of acetaldehyde, it will be 1.06. Formaldehyde, it will be 2280. In chloral, that is if we are having one hydrogen and three like CCl3, it will be 2000. Hexafluoroacetone, CF3 on both sides, it will be 12 lakh, right? Around 12 lakh. So the same structural features that favor or disfavor hydrate formation are important in determining the reactivity of carbonyl compounds with other nucleophiles, whether the reactions are reversible or not. Steric hindrance and more alkyl substituents make carbonyl compounds less reactive towards any nucleophile. So, this alkyl substituents will reduce the electrophilicity of the carbonyl carbon. Because of that, the carbonyl compounds will be less reactive towards any nucleophile. So, alkyl substituents can be CH3 or like CH3, CH3, CH, like anything, primary, secondary, or tertiary. It can cause make the carbonyl compounds less reactive towards any nucleophile. Now electron withdrawing groups and small rings make them more reactive. So if electron withdrawing groups like CF3, CCl3, etc. are coming, it will withdraw the electron from the carbonyl carbon. So it will become more electron deficient. Then it will be more prone to reaction. It will be more reactive. If it becomes more electron deficient, it will be more prone to reaction. So that is why in this case CH3, which is an alkyl substituent that is electron donating by a inductive effect, it will result in the it will result in the decrease of this electrophilic nature of the carbonyl carbon, and hence decrease the reactivity of that carbonyl carbon. That is why this compound will be having an equilibrium that will be less than 1. In all other cases, here CF3 is electron withdrawing group, CCl3 is electron withdrawing group, fluorine is electron withdrawing group. So that is why in all these cases, this carbonyl carbon will be electron deficient because of this electron withdrawing groups. That is why this center will be more prone to reaction with this water and result in the formation of this hydrate. But in this case, this CH3 will be electron donating in nature by inductive effect. So this carbonyl carbon will be less electrophilic. So hydration reaction will be less feasible. Is this clear? Is question 1 clear for everyone?
Clear, ma'am.
Okay. Now coming to question number 2. In hexane 2,4 dione, how many different monoenols are possible? So for enol formation to take place, there should be alpha hydrogens. right? So in this case, there will be here CH3, CH2, CH2. So this hydrogens that are adjacent to the carbonyls. So this adjacent to the carbonyl carbon. So this is carbonyl carbon. So this will be alpha carbon. This also will be alpha carbon with respect to both these ketones. And this CH2 or carbon will be alpha carbon with respect to this carbonyl. So here the number of alpha hydrogens will be here 3 plus here 2 plus here 2, which is equal to 7. So by abstracting each of the alpha hydrogens, it will result in the formation of phenols. So total there are 7 alpha hydrogen. So by abstracting each of that alpha hydrogen, it will result in formation of different monoenols. So the correct answer will be 7 as mentioned in the comment box. Is this clear? How enols are forming? A base will come and abstract the alpha hydrogen. It will result in the formation of the enol. So here we can see, we will solve one example. C, H, H, H. So the base will come abstract one of the protons. It will result in the formation of enol. O minus, double bond, H, H. So it can abstract this proton from the base and result in formation of the enol. H, double bond, H, H. This is clear, right? Any doubts?
I have some doubt.
Sure, you can ask.
Here we get, I think, four different types of monoenols because second and third replacement of hydrogen give the same type of monoenols.
These all are similar, but if we are labeling each of the hydrogens, if each of the hydrogens are separately labeled like HA, HB, HC, etc., by abstracting that
Yes,
proton, it will be resulting in different monoenol. So they have not mentioned regarding anything like it is labeled or something. So since the number of alpha hydrogens are 7, so each by abstracting each of the alpha hydrogen proton, it will result in the formation of one monoenol, right?
then it is okay.
So that is why we are considering it as 7. If they are
Okay,
identical or something like they have mentioned, so then we can say like here this will be considered like similar, this two can be considered like similar, and this two can be considered like similar. uh, then it can result in 4 or 3.
yes,
Now are you clear why we are selecting 7? Because the total number of alpha hydrogens that will result in the formation of enol will be 7. So that is why 7 different monoenols will be possible by abstracting each of the 7 different alpha hydrogens.
yes.
Okay. So the answer will be 7. Now coming to the third question. What is the correct order of equilibrium enol content of the following compounds? So what will be the correct order of equilibrium enol content of the following compounds? So I forgot to keep the options here. So you can tell me the order. You can see this is A, this is B, C and D. Accordingly, you can say the order. Which will be greater, then which will be the second greatest, third greatest, and which will be the least one.
CDPA.
C, C,
C, then D,
D,
B.
B, A. Okay.
Hmm.
So this is the correct answer. So what will be the reasoning that you can give for this?
Calculated total number of alpha hydrogen.
Yeah, we will be calculating the number of alpha hydrogens. Now then, if something like hydrogen bonding is possible, that will also be counted. So we will see the options. So this is requirement for enolization. In summary, any organic compound with an electron withdrawing functional group with at least one pi bond joined to a saturated carbon atom having at least one hydrogen atom may form an enol in neutral or acid solution. So this is just I have mentioned why enolization is occurring. So for that, the requirement is at least one hydrogen atom, alpha hydrogen atom, should be present. Then many also form enolates in basic solution. So mostly enolization is taking place in neutral or acid solution. In some cases, in basic solution also, enolates are forming. So for enolization or ketoenol tautomerism for taking place, hydrogen bonding, resonance, hyperconjugation, etc. we will consider. These are the factors we have to consider. Hydrogen bonding, resonance, hyperconjugation, and in some cases aromaticity, etc. So, have the tendency to stabilize the enolic form. That's why presence of all or one of these factors increases the enol content of a compound or makes the enol form more stable. In most of the cases, the keto form will be more stable than the enol form. But in some cases, the enol form will be more stable. So, which are the factors that will affect the formation of enol form or stabilize the enol form? That will be hydrogen bonding, resonance, hyperconjugation, etc. So, as you have mentioned, if the number of hydrogen atoms are increasing, number of adjacent hydrogen atoms, alpha hydrogen atoms are increasing, that will result in more hyperconjugation. If hyperconjugation effect is increasing, it will stabilize the enol form. Similarly, if hydrogen bonding is possible, in case of 1,3 dicarbonyl compounds, hydrogen bonding will be resulting. So, it will form a cyclic structure, as we can see here. If enol is forming, so this can result in a cyclic structure by means of hydrogen bonding. So if we consider this three cases with this will be least stable because in this case hydrogen bonding is not possible. But in other cases, as we have seen, this C will be having more number of alpha hydrogens, hence more hyperconjugation effect will be acting in case of C. That means 1, 2, 3, 4, 5, 6, 7, 8. 8 alpha hydrogens will be there. So this will be the greatest, this will be the compound having greatest enol content. Then comes this. We will, then comes this where this hydrogen will also involve in hyperconjugation. In case of ester, there are no hydrogens in this side that can involve in hyperconjugation. So this will be least. So the correct order will be C greater than B, greater than B, greater than A. Clear? So we will be considering the factors like hydrogen bonding, resonance, hyperconjugation, aromaticity, etc. while we are finding out the correct order of equilibrium enol content. So these are the factors that will be stabilizing the enol, thus increasing its content in the equilibrium state. Clear? Hello, is question 3 clear?
Clear, ma'am.
Okay. Now we will move to question number 4. So here they are asking to predict the plausible products in the following hydride addition reaction to 2-butanol. So we are given 2-butanol and we are treating it with lithium aluminium hydride. So what will be the products, or what will be the product? So they have given S2-butanol, R2-butanol, S2-butanol plus R2-butanol, none of the above. So which will be the possible products or product for the hydride addition reaction to 2-butanol? Any answers?
I think what S2 and R2 butanol as
Yeah,
a possible
both
products.
S2-butanol and R2-butanol will be forming, because this is not a like not a carbonyl compound which is already having a stereogenic center, as we have seen in the case of Felkin and model, etc. So here the mechanism will be like, here this is our carbonyl compound. So this LAH can add the hydride on the LAH can come and attack on in this fashion. So this aluminum will be having positive charge. This oxygen will be uh, adding to aluminum. So we will get this intermediate. So since this LH is having four like hydrogens that can involve in reduction. So here two more times it can take place, or three more times it can take place. Then upon hydrolysis, this bond will cleave and this AL H OH thrice will be leaving, and we will be getting this secondary alcohol. So this is the basic mechanism. So this addition can take place from both phases, rephase and siphase, because there is no other stereogenic center that is present on the carbonyl that is given in the question. So because of that, the LH addition can take place from both the rephase and the siphase. So it can result in both the R and S product in 1:1 ratio. Here we will get both R and S in 1:1 ratio. One reason is no stereogenic center adjacent to the carbonyl. That is why addition can take place from both the rephase and the siphase. So it will result in both R and S products in 1:1 ratio. So mechanism of LH reduction is clear.
Yes, ma'am.
Okay.
Yes, ma'am.
Now, so the answer will be C. We will be getting both S2 butanol and R2 butanol. Now coming to question number 5. Among the following compounds, one that will not show ketoenol tautomerism is. So we have seen that for ketoenol tautomerism to take place, there should be alpha hydrogen atoms present, right? If alpha hydrogen atoms are present, then that proton can be abstracted and the ketone will be converted into enol. So in the given compounds, one of the compound will not exhibit ketoenol tautomerism. So which will be the compound?
Second compound.
And what will be the reason?
Alpha hydrogen on bridgehead.
Huh?
There is one hydrogen, alpha hydrogen,
Yeah. Here.
and the bridging.
Yeah. So according to Brett's rule, if we are having alpha hydrogen on the Brett's rule, it cannot be abstracted because the resulting alkene, it will be in bridgehead position. That is not favored. So Brett's rule is an empirical observation that states that double bond can be placed at bridgehead of a bridged ring system. So in our case, if this proton is abstracted, it will result in formation of a double bond here, right? So this is not favored according to the Brett's rule. Bridgehead carbon cannot attain planarity due to strain, so we can't place the double bond there. As double bond makes this molecules sp2 hybridized, it should be planar. So here, because of strain, it cannot attain planarity in bridgehead position. That is why bridgehead carbon or at bridgehead position, the double bond is not favored. So this is called a Brett's rule. Brett's rule. So the correct option will be option B. This is clear for everyone. Actually, I am solving previous assignment question from August 2022, but most of the questions are repeated in August 2023 week 3 assignment as well. So if you are having any doubt, please stop and ask. Question 5 is clear.
Clear, ma'am.
Okay. Now we will move to question number 6. Hemiacetals are usually unstable whereas acetals are stable. Which has the most stable hemiacetals? So you are familiar with what is hemiacetals and acetals? Like if we consider this compound and if we add alcohol into alcohols or something to this, to result in OET, OH. So this is hemiacetal. And if this OH is also replaced by this OET, this is called acetal. So out of this four options, which one will form the most stable hemiacetal?
maybe second.
Second.
Yes.
Okay. But the correct answer is option number D. We will see why. So this is the mechanism of how a hemiacetal is formed. So we are having an aldehyde. So alcohol like ethanol, it can add on to this electrophilic carbon of the carbonyl group. Then this carbon oxygen double bond will break and this electron density will shift towards the oxygen. So this is the intermediate now. Now this proton on this ethanol will be abstracted by another molecule of ethanol and it will be neutralized. And this oxygen can abstract a proton from one ethanol molecule and it will result in the formation of a hemiacetal. So is this clear? How hemiacetal is forming? So now when we come to naming of these functional groups, excuse me, everyone please mute. Now when we come to naming of these functional groups, this is called hemiacetal. If one alcohol and one um, like OR group is there, either group is there, it is called hemiacetal. If both are like either groups, it is called acetal. This is in the case of aldehydes. And if we are having ketone instead of aldehyde and we are adding this alcohol into this, it will result in the formation of a hemiketal. And a cyclic hemiketal is referred to as lactol. So this is called a lactol. So hemiacetal formation is a reversible reaction and hemiacetals are stabilized by the same special structural features as those of hydrates. We have seen the case of hydrates, right? So, however, hemiacetals can also gain stability by being cyclic. Hemiacetals can also gain stability by being cyclic. When the carbonyl group and the attacking hydroxyl group are part of the same molecule, the reaction is now an intramolecular within the same molecule addition as opposed to the intermolecular between two molecules we have considered so far. So, if the hemiacetals are cyclic, it can be more stable. So this cyclic hemiacetals can result from intramolecular addition reactions. So in this case, here, this alcohol, it can undergo intramolecular addition to this aldehyde and it will result in formation of hemiacetal. So here 1, 2, 3, 4, 5. O minus, here OH plus. Now it will result in proton transfer and OH. So this is a cyclic hemiacetal. In other cases, the formation of cyclic hemiacetal is not possible. Right. In other cases, formation of cyclic hemiacetal is not possible. So this one will be more stable compared to the other hemiacetals. So correct option will be option B. Is this clear?
Yes,
Can
ma'am.
you
Okay.
please can you please tell increasing order of stability out of
What?
these four options? Increasing order. Can you explain?
Okay, for this four options. Okay, we can
Yes,
see.
ma'am.
We have seen this is similar to that of the hydrates. So we have seen if alkyl groups are present, alkyl groups will decrease reactivity, right? Decrease the rate. If electron withdrawing groups are present, that will increase the rate. So here this will be an electron withdrawing group, phenyl group. Phenyl is an electron withdrawing group. So this will be more prone to attack from uh, a alcohol, and in this case if hemiacetal is forming, so this one alcohol will be there that can coordinate with this and result in hydrogen bonding. So I think the least one will be for a. A will be the least one, then comes C, then comes B, and then D. It will be okay, right? Here formation of the cyclic structure will be possible, so it will be
Okay,
the
okay.
most stable. Then here the phenyl group will be electron withdrawing, so the carbonyl carbon will be um, more electrophilic, so formation of hemiacetals can take place, so it will be the next stabler one. Then in case of C, if hemiacetals are forming, it can result in hydrogen bonding formation, so it can result in stability of the hemiacetal, so it can be C, next stable. And here these all are electron donating groups by inductive effect, so this carbonyl carbon will be electron rich kind of, so it is less electrophilic, so the formation of hemiacetals will not be feasible, so it will result in least stable hemiacetal. Clear?
Yes, ma'am. Thank you.
Okay, now coming to question number 7. So this is question number 7. Predict the major product of the following addition reaction using Felkinan model. So here they have given this carbonyl compound with an adjacent stereogenic center here, and they are carrying out reaction with methyl lithium and finally hydrolysis. So it will result in P and Q, which is major and minor, in the ratio 3 is to 1. So they are asking us to find out what will be the major product. You can try working out the Felkinan model and see the answer. Now let us see the mechanism. Then you will be able to predict. So we have seen, so this is similar to that. Uh, the adjacent carbon is having pH, CH3 and H, which is similar to the example we have seen in the case of Felkinan model. So this is the human projection representation of the compound that is given to us. So the carbonyl, it is having a hydrogen, and adjacent to that the larger group is phenyl, medium group is CH3, and the smaller group is hydrogen. So this is same as that. So we draw the carbonyl group, the pH group, which is the larger group, it is drawn perpendicular to the carbonyl. Then two possibilities are there. One hydrogen can be below, methyl can be above, and if we rotate it, it can result in this conformation as well. And we have seen that in the attack of the nucleophile will be taking place at an angle of 107 degree, which is the Bourguignon units angle. So here the nucleophile can attack from here or here according to the Bourguignon units angle. So this will be unhindered position because here there is a smaller group, that is hydrogen. And here if the nucleophile is coming in this direction, here it will be closer to that of the phenyl group and it will be hindered. And here if the nucleophile is coming in this fashion, it will be closer to that of the phenyl group and it will be hindered. And when the nucleophile is coming in this fashion, it will be closer to that of the methyl group and it will be hindered. The three brown flight paths are hindered by phenyl or methyl. The black flight path is the best. So we have chosen that the nucleophile will be coming and attacking from this side. So now the nucleophile, in our case, it is CH3Li, right? So the nucleophile will be CH3 minus. Nucleophile will come and attack in this position. Now this double bond will break. It will result in formation of OH. So it is drawn in this fashion. Now we are redrawing it. How we are redrawing? We are redrawing in such a fashion that, see, these groups are coming in the plane. So first we will see nucleophile. Now the hydroxyl group is coming above. Hydroxyl group is coming above. Then this methyl group, it is also coming above, and then pH. So it is similar to that, right? Both the groups are in the same direction. If we rotate, it will be like pH, Me, OH, Nu. Here the Nu will be methyl. So the correct option will be this option B, because here in our example it is given like this, both groups are coming in the same direction, methyl and OH, that are syn to each other, right? The methyl group and the alcohol group are coming syn to each other. If we are considering this example, if we rotate it if we rotate it in 180 degree, the methyl group will be coming below the plane and the OH group will be coming one group. Let me erase sequence. So this is clear, right? We are seeing this nucleophile, then carbon. This is behind carbon, and this is phenyl group. So this is in plane. This we are assuming to be in plane. Then this alcohol is above the plane, and this methyl group is also above the plane. Since we are viewing from this direction, so we drew it like this. Now we rotate it. If we are rotating it in 180 degree fashion, if we rotate it in 180 degree, it will be like pH, then this methyl will be coming below the plane and hydroxyl will also be coming below the plane. So this will be the resulting compound. Or we can see this. If we rotate in 180-degree, this compound will be, this both methyl and hydroxyl will go below the plane. So the correct option will be option B. Filkinan model is clear.
Yes, ma'am.
Okay. So correct option will be option B. If you are having any doubts, you can ask. If no doubts, we can proceed to question number 8. Can we proceed?
Yes, ma'am.
Yes, ma'am.
Now this is the question number 8. In the following nucleophilic addition reaction, so here there is a carbonyl, and adjacent to that there is an electronegative oxygen atom which is protected by TBDPS, TBU-PH2SI, that is TBDPS, tetrabutyl diphenyl silyl. So now we are adding this nucleophile at minus 78 degrees Celsius so as to ensure the stereoselectivity, and TBAF, it will be for deprotecting this TBDPS group at a later stage. So we will be getting two products, P and Q, which is major and minor. So what will be the major product? That is P. We can go to mechanism so it will be clear to understand. So we have seen C-plaque model in the last lecture, right? So if there is a bulky group having electronegative atom, so it will come in perpendicular direction to that of the carbonyl. Now now what will happen? Now the addition of the nucleophile will take place from this unhindered direction. So this will come in this fashion, and this will go and attack. So it will result in the formation of this product, and if we redraw it to put the longest chain in the plane of the paper, we will get this compound. So this is the C-plaque model, and we will see the case with our compound. We will draw the mechanism now. One second, let me put this on chart. And this is the mechanism for fluoride mediated deprotection of silyl ethers, which we are carrying out in presence of TBAF. TBAF is a fluoride source, tetrabutyl ammonium fluoride. So this fluoride will be having affinity towards silicon. It will come and attack on silicon, and this OR will be leaving out. So this will be the intermediate that will be forming upon addition of the fluoride. Then OR will leave out. That will be our alcohol. It will be leaving out, and this compound will be forming. Fluoride and silicon will be forming a complex. So this is how the alcohol group will be deprotected from the silyl protection. Now we will see the mechanism for our case. So we are having carbonyl group. So we will draw we are having carbonyl with a CH3. Now if we are looking from this direction, here the hydrogen, it will be on our right hand side, and OSI PH2 TBU, it will be on our left hand side, and this methyl group we can draw close to that of the carbonyl. Now if we draw the conformation that is more stable with this group, that is with this electronegative oxygen that is protected with a bulky group perpendicular to that of the carbonyl, it will come in this fashion: CH3 O Si PH2 TBU hydrogen CH3. Now so this compound, it will go and attack on this carbonyl. So this is the unhindered position. Burgee units angle, unhindered position. So this will come and attack in this fashion. So we can write O this will be OH CH3. Back carbon we will draw as it is H CH3, and this can be written as OR. R is that bulky group protecting this. So now we have to redraw it in such a way that the bulky chain or the longest chain will be coming in plane. So we can rotate this front carbon such a way that the CH3 and this group are coming opposite to each other. So we rotated it. Now CH3 will come here, and this alcohol will be coming here. Bicarbon remains as it is. Now this is our longest chain, right? Double bond. So alcohol is coming below and CH3 is coming above. Alcohol is coming, we are looking from this direction. So if we are looking, the CH3 is towards us and alcohol is away from us. So CH3 is coming towards us and alcohol is coming away from us, and in the back carbon this alcohol is coming towards us, or is coming towards us. So it is written as OR, and this is CH3. So this is our product. So if we are treating it with TBAF, this R group will be deprotected and we will get OH, OH and CH3. Clear? So in our example, one of the alcohol will be above the plane, other alcohol will be below the plane, and the medial group will be below the plane. See here, both alcohols are anti to each other. That is what we have to see. So the correct option will be option A. Mechanism is clear? You can try out working the mechanism again and again, then it will be thorough. Any doubts regarding the product?
No, ma'am.
Okay. Now we will move to question number 9. So here, which of the reaction forms the most stable acetal in the given condition? So here they are asking which of these reactions will result in more stable acetal. So here they have given acetone plus ethanol in presence of H plus, it will give one acetal. Then acetone plus ethylene glycol in presence of H plus, it will give one acetal. Then here they are having this cyclohexanone with two double bonds treating with ethanol in presence of H plus, it will give acetal, and benzophenone in presence of ethanol, if we are treating with H plus, it will give acetal. So which will be the most stable acetal?
Product of first one.
Hmm? Which one? A or B?
A.
Actually, answer will be B because ethylene glycol will give cyclic acetal. So that will be more stable. So this is how acetal is forming. First hemiacetal will result, and this in the presence of acid, this will be forming OH2 plus and it will leave by formation of oxonium ion. Then again alcohol will attack and it will result in the formation of acetal. Hemiacetal formation is catalyzed by acid or base, but acetal formation is possible only with an acid catalyst because an OH group must be made into a good leaving group. So here in this case it will result in formation of OET, OET. In this case it will result in formation of cyclic acetal. Here also it will result in formation of OET, OET, and here OET, OET, and pH. So this cyclic form will be the most stable one. Correct answer will be option B. Clear?
Yes, ma'am.
Okay. Now we will move to question number 10. So here the major product formed in the following reaction is. So this is our carbonyl compound. It is treated with Z and pH4 twice. So we will be getting one of the four mentioned options as the correct product, as a major product. So we have to find this. So here the chelation mechanism, as we have seen in the summary session, the chelation mechanism will be taking place. Zn2 plus can undergo chelation, and here methyl OMe is there and this oxygen is there. So this can undergo chelation with the Zn2 plus. So what will be the mechanism that will be taking place here? So first we will see the general mechanism. So here is another example of a reversal in selectivity that can be explained using a non-chelated Felkinan model with Na plus and a chelated model with Mg2 plus. So here we can see if we are treating with NaBH4, this will be the major product and this will be the minor product. And if we are treating with Me2Mg, where the nucleophile is Me, this product, which will be the which was the major product in case of NaBH4, is now only 1%, and the major product will be this one, 99%. So here chelation is taking place in the presence of Mg2 plus. Two things are added for chelation to occur: a heteroatom with lone pairs available for coordination to a metal. So here this OMe. This is an heteroatom having lone pairs. So it can coordinate with the metal. And a metal ion that prefers to coordinate to more than one heteroatom at once. So these are the requirements for chelation to take place. First, a heteroatom with lone pairs available for coordination to a metal, and a metal ion that prefers to coordinate to more than one heteroatom at once. So the metals that are commonly involved in chelation are Li plus, which is involved in chelation sometimes, then Mg2 plus, Zn2 plus, Cu2 plus, Ti4 plus, Ce3 plus, Mn2 plus. These all involved in chelation, and those that does not involve in chelation are sometimes Li plus and often Li plus and Na plus, K plus, etc. These does not involve in chelation. So if chelation is occur, what will happen with the mechanism? So here we are having the carbonyl compound, and here we are having Me2Mg as the nucleophile. So this Mg, Mg2 plus, it is a metal that can undergo chelation, and here there is a group heteroatom having lone pairs. So now what will happen? So we have seen that this OR will be the group that is perpendicular as R is large. Normally, according to Felkinan model, this OR will be perpendicular to the carbonyl. OR is R is a large group, so OR should be perpendicular to the carbonyl group, and nucleophile will be attacking in this direction as per unhindered approach, and it will result in the formation of this product. This is the major product by non-chelation, that is Felkinan control. Now, according to chelation control, what will happen? This will move towards this side. This OR will move towards this side, and the hydrogen will shift in this direction, and Me will come perpendicular to that of the carbonyl. Now the nucleophile will be attacking in this direction. So instead of attacking from this space, now nucleophile is attacking from this side, and this OR and O are chelated by the Mg2 plus. Here R should be a small group for chelation to occur. So it will result in this major product by chelation control. Now we will see the mechanism for our reaction. So we have been given OMe, which is having a lone pair of electron, and our metal is sorry and our metal is excuse me and our metal is Zn2 plus. So we can draw the Newman projection like carbonyl CH3, and if we look in this direction, so here there will be one hydrogen as well. So we can draw like OMe as the bulky group, hydrogen, and then methyl. So this will be the normal structure that will undergo Felk- normal Felkinan model, which can undergo nucleophilic addition. So nucleophile can come and attack in this direction, and it will result in the product. But now, since this can undergo chelation, this will move closer to that of the carbonyl, and this will shift in this direction. So the structure will be double bond O CH3 hydrogen Me OMe, and this can chelate with Zn2 plus. So now the nucleophile will be coming and attacking from this direction. Nucleophile is hydrate from BH4 minus. So the hydrate will come and attack in this direction, and it will result in the formation of OH, CH3, H, and the backside carbon will remain as it is. OMe and hydrogen. So now if we redraw it, it will come like CH3. This carbon is, this OH is above the plane according to our, this methyl group is also above the plane, and then OMe. So these are coming in the same plane. Clear? So this is the product. So which will be the major product? OH, CH3, H, methyl, hydrogen, OMe. Hydrate is coming in this direction. Both the hydrogens are in the same phase. So what will be the major product? Both this methyl and hydroxyl are coming in same direction. 1 second. This model is clear for you, right? This will be the structure that is most favorable for the addition to take place. But since chelation is present, this will move in this direction. This OMe will be bulky group than that of the methyl. So this will move closer to that of the oxygen, and we will get the structure. This OMe and oxygen will coordinate with Zn2 plus. Now the nucleophilic attack will take place in this direction, and the nucleophile will be hydrate from BH4 minus. So the hydrate is adding at this position. So now what will be the structure? This Me, this hydrogen and this OMe will remain as it is, and here the hydride is coming and attacking, then OH, and then this methyl group CH3. So if we are considering these groups are coming in the same plane, then we can write Me, and the hydroxyl is coming above the plane, then methyl is also coming above the plane. If we are seeing from this direction, methyl is coming also above the plane, then OMe. So the correct option will be option A. I have written here the wrong answer. Option A will be the correct answer. Clear?
Yes, ma'am. Yes, ma'am.
Okay. So this will be OH. Now coming to question number 11. Which of the following has greater enol content than the corresponding keto counterpart? This is similar to the question that we have discussed earlier, which will be having greater enol content than the keto counterpart. So we have to take into consideration these things: resonance, aromaticity, hyperconjugation, polarization, and like hydrogen bonding. So these factors we have to take into consideration: resonance, aromaticity, hyperconjugation, polarization, hydrogen bonding. So out of these four, which will be having greater enol content than the corresponding keto counterpart?
Option B.
Option B. Here, resonance is possible, but in case of hyperconjugation, only two alpha hydrogens are present, right? So C will be the correct answer. It can result in hydrogen bonding after formation of phenol, and there will be 1, 2, 3, 4, 5, 6, 7, 8 alpha hydrogens. So the correct option will be option C. This is clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now coming to question number 12. How many tautomers can be drawn for the following ketone? How many tautomers can be drawn?
2.
Two. Like here, one alpha hydrogen is there, and here also one alpha hydrogen is drawn, can be drawn. So by abstracting this alpha hydrogen, it will result in one ketoenol form, and by abstracting this alpha hydrogen, it will result in one ketoenol form. The correct option will be 2. Here we will consider the number of alpha hydrogens. In case of ketoenol forms, this is one of the important factor we have to take into consideration: number of alpha hydrogens. This is clear, right? Now coming to question number 13. In the reaction, CH3CHO, that is plus HCN gives X. A chiral center is introduced. So here we are adding Cn minus. So this can be called prochiral. We will result a it will result into a chiral product CH3 OH H and Cn. The product S is, what will be the nature of product X? Is it levorotatory, dextrorotatory, a meso compound, or a racemic mixture?
Racemic mixtures.
Racemic mixture will be the correct answer because we have seen similar reaction where we have done LH addition, like reduction with LH. So in that case, we have get both the S and R isomers in 1:1 ratio. So the if S and R products are obtained in 1:1 ratio, then it is called a racemic mixture. So the correct option will be option 4, that is racemic mixture. Now coming to question number 14. HCl not produce a chiral compound with. So four options are given. So here they are asking, when HCN is added, one of the compounds given here will not result into a chiral compound. Which one is that starting material which will not result into a chiral compound?
Option 1.
Yeah. Option 1 is having here two ethyl groups. So if we add HCN into this, it will result in formation of OH, CN, ethyl, ethyl. So here all the four groups are not different. This ethyl is common. So this is not a chiral center. So option 1 will be the correct answer. HCl not produce a chiral compound with this ketone. Now coming to question number 15, which is the last question in this weekly assignment session. So arrange them in increasing order according to their reactivity towards HCN. So here four different groups are given: acetaldehyde, acetone, di-tert butyl ketone, methyl tert butyl ketone. So which will be more electrophilic center, which will be more reactive towards HCN. So according to that, we have to arrange it in order. So what will be the correct option?
Option 2.
Option 2 will be the correct answer. In case of acetaldehyde, aldehyde functional group is there and only one CH3 will be there. CH3 will be electron releasing group. So CH3 can reduce the electrophilicity at this carbonyl center. In case of acetaldehyde, only one CH3 is there. In case of acetone, two CH3s are there. In case of di-tert butyl ketone, we are having tertiary butyl group. So this is the tertiary butyl group which is having 3 CH3s. So this is more electron releasing than that of a normal CH3. So di-tert butyl ketone, it will be having 2 tertiary butyl group, and in methyl tert butyl, 1 tert butyl and 1 methyl group will be present. So when we are arranging it in order of reactivity towards HCl, acetaldehyde will be the most reacting one. Then comes acetone. Then comes methyl tert butyl ketone, and then di-tert butyl ketone. So the correct order will be di-tert-butyl ketone have less reactivity than methyl-tert-butyl ketone, less reactivity than acetone, less reactivity than acetaldehyde. So here we have to consider the inductive effect by the electron releasing alkyl groups. So inductive effect of the alkyl groups will reduce the electrophilicity of the carbonyl center. That we have to take into consideration. Then we will be able to arrange it in the increasing order of reactivity. Clear? Any doubts?
No, ma'am.
If you are having any doubts, you can feel free to ask in the comment section of our YouTube channel. These videos will be uploaded in the YouTube channel. You can feel free to see it, and if you are having any doubts, you can ask in the comment section. Thank you all.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you very much, madam.
Thank you.